right triangle is of significant importance to us in this continuing discussion of the trigonometry. So I hope that you pay particular attention to these relationships between the trigonometric functions and a right triangle. Okay, so we'll begin with this basic drawing that I have. We have a right triangle, so we have this 90-degree angle here. If you read books, the books are written in a way that sometimes they use letters, variables for the measure of each side. Sometimes they call them by where they're located with respect to the angle that we have some with respect to the angle given in that triangle. So for example, for the sine function, we can say for this angle, sine of theta, we can either say it's the opposite side or y. We can say y over hypotenuse. So that's one way of writing the measure of sine of theta. Or some books write it as sine of theta is equal to the opposite. They mean the side of the measure of the side of the triangle that is opposite to that angle divided by the hypotenuse. I personally prefer it this way. The reason being, when we get to polar coordinates, then the variables x and y become important, more important than whether it's the opposite side or the adjacent side, for that reason. But both types of formulas are equally valid. So you pick whichever way helps you understand this connection better. Okay, so then let's write down the cosine function for this angle in this right triangle. So we have cosine of theta would be equal to the x divided by the hypotenuse. We can write it like this, or we can say cosine of theta is equal to the adjacent side, or adjacent divided by hypotenuse. All right, so the length of the adjacent side divided by the length of the hypotenuse. We can next talk about the tangent function. So the tangent of theta can be written as the opposite, or y over x, or you can think of it as tangent of theta equals opposite divided by the adjacent side. Okay, so again, this way of writing the relationship in the right triangle with the tangent theta is very helpful when we get to the polar coordinates later on in this course. Okay, so let's write down the cotangent of theta. So remember the relationship between cotangent and tangent? Remember how they're connected? Well, they are reciprocals of each other, right? So if tangent is y over x, then cotangent is x over y. And cotangent of theta would be equal to, so it would be the opposite, so it would be the adjacent over the opposite. Okay, that's all shown in the figure. Okay, so let's write the last two functions, which are the secant and the cosecant functions. So we have for the secant function, secant of theta. Remember the connection between the secant function and one of these other functions? Remember that? The secant is the reciprocal of the cosine function. Oops. Like that. So the lens just dropped. Secant of theta is equal to reciprocal of the cosine function, so 1 over cosine theta. So, but the cosine function was equal to adjacent divided by the hypotenuse, right? So reciprocal of this would be the secant of theta equals, take the reciprocal of this, you'll have the hypotenuse divided by the adjacent side. Like that. Okay, finally, the cosecant of theta. So do you remember how cosecant function was related to one of these other functions? Do you remember which one it was? If you said cosecant function is the reciprocal of the sine function, you're absolutely correct. 1 over sine of theta, or we can write it as, but the sine was y over hypotenuse, so hypotenuse over y, right? Reciprocal of it. Like that. So this is all the relationships of the 6 basic trigonometric functions and the right triangle. So let's see some examples, some easy examples just to warm up. So we want to find the exact values of these 6 trigonometric ratios for the following figure. Which is as follows. So we're going to have this figure given to us. So we have this right triangle, right? This being the 90 degrees. We have that line as the hypotenuse. We are told that this is the angle theta. We are told that the measure of this side, or the hypotenuse, is 7. And this one is 24. And this one is 7. Okay. So I want to do a quick check of if this is working. I'm pretty sure it should be correct, but let's check it, because that should satisfy the Pythagorean theorem, right? So 7 squared is 49 plus 24 squared. We get 625, and 25 squared is, of course, 625. So these numbers are valid For a second, I doubted it, and I had to check. And so what we want to find is find the exact values of these 6 trigonometric ratios for the following figure. So sine of theta is asked of us. Then cosine of theta is asked. Then the secant of theta, we want that. And of course the tangent of theta, we want to know that. And the cotangent of theta, and of course cosecant of theta. Okay, so from this page, we talked about how that relationship works, right, with respect to each trigonometric function and the sides of a right triangle. It's not very popular to memorize these things, but believe me, if you memorize these relationships of these 6 trigonometric functions and the right triangle, your task in this course will be infinitely easier. So I recommend that. All right, so sine of theta would be the opposite side divided by the hypotenuse, or y divided by the hypotenuse. So this would be 7 divided by 25. I'm just going to leave it like that because I want you to, as you look at this page, after I post this on Canvas, you can look at each trigonometric function and connect it with the relationship that it has with each side of the right triangle. So that's important. So I'm not going to calculate the decimal value for it for that reason. So cosine theta is equal to the adjacent side, or x 24 divided by the hypotenuse. Like that. Secant theta. Remember, this is the, which trigonometric function was this connected to? I keep reminding you of this. Right, if you said this is the reciprocal of the cosine function, you're absolutely right. So all we have to do is flip this, 25 divided by 24. And with the tangent is equal to the opposite side divided by the adjacent side. So 7 divided by 24. One thing I want to add to this page. So here we said that, okay, tangent of theta is equal to y over divided by x, or opposite divided by adjacent, which is true. But I want to add something else to this. So tangent of theta is also equal to the ratio between sine of x divided by cosine of x. That is also a very important relationship between these 3 trigonometric functions as we move forward. And the cotangent function, as you know, is the reciprocal of that value. So cotangent of theta would be flip this, right? Take the reciprocal of it, or cosine of x. Well, I wrote x, sorry, this should be theta. Theta, theta. And this is theta over sine of theta. So I wanted to add that because this is a relationship between 3 basic trigonometric functions. Okay, so that was also important to remember. Okay, so for cotangent of theta, this is the adjacent, that side, adjacent to the angle, divided by the opposite. So 24 divided by 7, or the flip, or the reciprocal of what we have for the tangent, right? Like that. And cosecant, do you remember which other trigonometric function was this connected to? If you said to sine of x, you are correct. So cosecant of theta is the reciprocal of sine of theta. So this would be, for the sine we had 7 over 25. So all we have to do is say 25 over 7, like that. Okay, so as we go through this, please take the time to spend 15 minutes, 10-15 minutes, maybe not every day, but say at least twice a week, 15-20 minutes, 10-15 minutes twice a week, and try to memorize the sine, cosine, tangent, cotangent, secant, cosecant for these special angle values. Okay, I just wanted to remind you of that. Okay, so let's solve a right triangle. So note that all of its 3 angles and 3 sides. So we're quite familiar with what solving an equation means, right? But this is solving a right triangle means that we need to find the measure of all of its 3 sides, how long they are, and also the 3 sides, 3 angles and 3 sides right here. So how long the sides are and what's the measure of each angle. That's what it means to solve a right triangle, like that. Okay, so let's do an example on this. So we want to solve, so here's an example. We want to solve the following right triangle. Let me move this up, so like that. Okay, so let me draw this right triangle. It looks like this. First of all, let me just like that. So this is our example. And we have a side that looks like this and a perpendicular side to this, as best as I can draw it, like that. So this is the 90-degree angle, and of course this side, that is the hypotenuse, like that. Okay, let's assume, so this is the given information. We know that this is 90 degrees. We don't know what this theta is, so I'm going to put a question mark there. But we know that this angle is 68 degrees. That's one is given. We also know that this is A, this is point A, B, and C. And we also know that the length of this side is 1,000. 1,000, some kind of unit, right? So we want to solve this, which means find the only angle that is missing. We know that is 68 degrees. This is for sure, so this is 90 degrees, and we want to know that. And then once we have that, we also want to know what is the length of AB and what is the length of BC. So which measure do you think it's the easiest to find right away? Well, if you said this theta, you're absolutely correct, because the summation of all angles within any triangle should be 180 degrees, right? So we know that theta will have to be 180 minus the summation of these two angles. So 180 minus 68 plus 90 degrees, and this would be equal to, what did I get? So I got 22 degrees. Can we change this to radians? Absolutely. You can, but I'm going to leave it as degrees because what we were given was in degrees. But you could change this to radians by simply multiplying this by pi over 180. Again, you can convert this to radian angle by multiplying this number by pi over 180. Okay. So now the other sides, so we're looking for AB and BC, right? So once we have the theta, things are going to simplify greatly, right? Because we know that AB, well, let me write it like this, first of all. We can say that sine of theta is equal to AB, which is the opposite side to that, AB over the hypotenuse, which is AC. Okay? Okay, so we know that theta is 22 degrees. So therefore, we have sine of, so this is finding AB. Finding AB. This was finding theta. Like that. So we have sine of 22 degrees is equal to AB, which is what we're looking for. AB divided by AC, the hypotenuse, which is 1,000. Okay, so from here, the sine we have, we have AB, cross multiply because you have one fraction on that side and one entity on this side. We know that the denominator here is 1, so AB times 1 is AB, and then sine of 22 degrees times 1,000. Okay, we use our calculator, and then I have rounded my number to 374.61. Okay, so that is the length of AB. Okay, so now let's find BC, right? This length. So BC is the side adjacent to this angle theta, right? So which trigonometric function can we use for that? Do you remember? Which trigonometric function makes use of the adjacent side divided by the hypotenuse? If you said the cosine function, you're absolutely correct. So we have cosine of theta equals, cosine of theta equals BC divided by the hypotenuse, which is AC. Okay, so let's substitute for these. This would be cosine of 22 degrees. Equals BC divided by AC, which is 1,000. Okay, like that. So we have BC equals cosine of 22 degrees. Again, we cross multiply because the denominator here is 1. We have one fraction on the other side. BC times 1 is just BC equals cosine 22 degrees times 1,000. Like that. So we have 927.18. Like that. Okay, so that is BC. Let's work on one last problem in this section. It's a word problem. It's an interesting word problem that makes use of the trigonometric relationships and with the right triangle. 3. I tend to underline my quantities. This is a habit that I have. As I read through a problem statement, I just underline the quantities just so that they stand out. An observer 600 meters away measures angle of elevation to the spotlight to be 45 degrees. And given that, we want to find the height h of the cloud cover from the ground, right? Like that. Okay, so this is not a very complicated scenario, and whenever I have a simple scenario like this, I always like to draw a picture of it. So let's do that. So we have some clouds, say some clouds here, like that. So we have some cloud, and we have, what else we are given? A worker shines a spotlight upward at an angle 75 degrees to us. So we have some worker here standing, right? Like that. And this worker is shining a ray of light or spotlight onto this cloud cover at a 75 degree angle. So like that, something like that. So that's 75 degrees with relationship to the ground. So let me draw the ground for this. Something like that, right? So this is the ground, and this is the worker, and we are told that this angle here is 75 degrees angle, right? And then we are also told that, and from the horizontal, so that's, or the horizontal, or ground, let me, or say horizontal ground, and observer 600 meters away. So let's say what do I want? I want maybe here. Let's say this is an observer. So here, so let's say that's an observer. This is observer. And we are told that this is 600 meters. So from here to here, we are told that it's 600 meters away. The observer is 600 meters away from the person who's shining a spotlight on the cloud. Okay, and then an observer 600 meters away measures the angle of elevation to a spotlight to be 45 degrees. So this observer measures this angle from himself to this spotlight to be 45 degrees. So let's draw that. So that is like that. So that is 45 degrees. This is all the known information. So that's 45 degrees. And we want to know find the height h of the cloud cover from the ground. That would be this height. So this vertical height from the cloud to the ground, like that. Okay, and so let's call this h. H, or the height, is the question mark. So this is our cloud cover. Okay, so it's clear from this picture that if you looking at this height that we're looking for, at this line connecting the cloud vertically to the ground level, we have a right triangle here, right? So if you drop a line vertically from the cloud to the ground, we know that this angle is 90 degrees. Okay, that's what we can quickly say. And if this is 45 degrees and this is 90 degrees, then this has to be what would be the measure of this angle? Can you calculate that? If this is 45, this is 90, what would this angle have to be? Given that all the summation of all the angles within a triangle, and I'm talking about this triangle, defined by this vertical dashed line, and here, the summation of all these angles should be 180 degrees, so we have 90 plus 45, so this must be 45. So let's write that down. Let's call this theta 1, right? That angle. Note that theta 1 should be equal to 45 degrees, right? Because because 180 degrees minus 90 plus 45 degrees would be equal to 45 degrees angle. And this is theta 1 equals that. Okay, so we know that right away. This is a very, very important conclusion or finding, because if you have any triangle that has two 45 degree angles and the other being 90 degree, then this is an isosceles triangle. So let's write that down. Therefore, the triangle, let's name these. So let me call this A. I'll call this point B. Sorry for this is getting too crowded on my drawing. So this point A, this point B, and this, let's call this D, and the point that is at the cloud, let's call that C. So A, B, D, and C. Okay, so we're looking at the triangle ABC. All right, ABC must be an isosceles triangle. That is, two sides are equal to each other. So the significance of this then, it means that H and AB are equal to each other, H and AB. This side is opposite this 45 degree angle, and this side, AB, is opposite this 45 degree angle. Okay, so those two sides must be equal to each other. So H equals AB. Very important conclusion from this, that theta 1 is a 45 degree angle. Okay, so now we can make use of this relationship that we have between the trigonometric functions and these sides of a right triangle. So this is also a right triangle, right? This one on the other side is also a right triangle. So we can say that this side we don't know, so let's stay away from the hypotenuse. We have this side which is adjacent to 75 degree, and we have this side which is opposite of it. So let's stick with these two sides. So that would be we can say that tangent of 75 is the opposite divided by the adjacent. Okay, that would be BD. So let's write that down. I don't know if I can keep the figure and the rest. I'll scroll up and down so you can see things. So for now, we're going to take tangent of 75 equals the height, which is H, divided by the adjacent, which is BD. So tangent 75 degree is equal to H divided by BD. Okay. So let's bring this down and have a look at it, because here we have two unknowns. We have two unknowns here, so we can't find H unless we know what BD is. Well, then let's note that BD, that side from here to here, is equal to 600 minus AB, right? BD is equal to the entire length of this distance, 600 meters, minus AB. So let's replace BD with that. So tangent 75 degrees is equal to H divided by 600 minus AB, right? BD is equal to 600 minus AB. So we have that. But right now, we really didn't change anything from here to here because we still have two unknowns. So we need to reduce this equation to one unknown, which is h, so we can solve for it. But if you notice, in the drawing, we just determined that this triangle, ABC, is an isosceles triangle, meaning that H and AB are equal. So yeah, we can come back here and replace AB with H, because AB is equal to H, because this was 45-degree angle, this is 45-degree angle, and so this is an isosceles triangle, which means these two sides, the H and the AB, are equal. We couldn't say that about this, right? Because this is 75, this is 90 degrees, so that'll be 15 degrees. So we don't have an isosceles triangle on the right, but we have an isosceles triangle on the left. Okay, so let's take advantage of that. So we have tangent of 75 degrees is equal to h over 600 minus h. All right? So the rest is just doing the algebra, because now we have one equation, one unknown, and we can certainly solve for this h. So let's do that. So the denominator here is 1. We can cross multiply. We have h times 1 is h. So I'm going to write that here. H equals tangent of 75 degrees times all of that. Minus h. Okay, so now if you use your calculator and find what that is, that's going to be equal to 3.732, and I must have rounded that number. I bet I rounded it. So if we have, so let's take tangent of 75 degrees. So notice how many decimal values? So I rounded this number to 3.732. Right? That's what I did, which is fine for this calculation. And then times 600 minus h. Okay, so we have h equals 3.732 times 600, and we get 2,239.2 minus 3.732h on the other side, right? So move all the h terms to one side. So this arrow should be actually here, right? And then we come back this way. So then we have h, let's see, so let's combine. We have 2239.2. Move this to the other side and add it to this. The coefficient here is 1. So 1 plus 3.732, it's going to be, when you move this, this is going to be positive, right? On the other side, it's going to be positive 3. So adds to this one, we get 4.732h. So h is equal to 2,239.2 divided by 4.732, and h is equal to 473.2 meters. Okay, so that's the height of the cloud cover. So I'm sure you convert that to feet, it'll be something over 1,300 feet. I'm sure it's like 14, maybe even 14, something around 1,400 feet. Okay, So thank you for persisting through this lesson on section 6.2. And this wraps up that section. And next time when we meet, we will talk about section 6.3. Until then, have a nice day, and I'll see you next time.